So I'm Nenad, and I'm really glad to be here tonight. And I will be talking about how to add search suggestions to your Laravel application. So, but before we start, let me briefly introduce ourselves. So we are a Croatian-based company located in Croatia, and we consist only of two. The other guy is Sasha. He's also tonight here. Since we are using a lot of open source tools, we try to give back to the community. So we created the TNT Search package, and it got a lot of attention. It has already over 1,000 stars on GitHub and over 70,000 of downloads. And a lot of PHP CMSs seem to be using it. So this was a package that was missing in the PHP community. So it was natural to create it and to open source it. Okay, so what are we going to create? You probably all are familiar with the did you mean functionality from Google. So when you enter a typo into Google, he will suggest you the did you mean the correct form. So we'll talk about how to achieve this. The presentation is divided into two parts. One is the theory behind it, and in the second part, we will touch the code for this. So this is actually in information retrieval. This is called tolerant retrieval, and it's used for other cases like spelling correction, search suggestions, and wildcard queries. So once we are done with this example, maybe you will find some use cases to implement this. So in order to achieve this, we will need to go through some algorithms that are needed for this. So there are a bunch of distance calculation algorithms, and we will briefly go through some of them. So probably a lot of you are familiar with Levenstein distance, which is basically a function that tells us how many changes, edits you need to do to get from the source string to the target one. So it returns a number of changes required. The good thing is that this Laravel distance function is built into PHP. So that's a good thing. Then we have the Jara-Winkler distance, which is similar to the Levenstein distance, but instead of returning a number from of how many changes you need, it returns a value from 0 to 1. So if you have two strings, 1 means that they are identical, and 0 that they have no similarity. And the good thing is that Jara-Winkler gives favor to prefixes. So if a string starts with the same letters, it will be more likely to be similar. Then we have the Euclidean distance, which is the distance between 2 points in Euclidean space, and n-grams. We'll cover this in a couple of further slides. And cosine distance, this is if we take two strings and convert them into vectors, we measure the angle between those strings. Also a good thing. Okay, what are n-grams? Just to make it very, very simple. The n represents a number. So if we have a sentence or a string, a word, we will break it into group of n. So for example, if we need to break a string into trigrams, then we break it into group of 3 letters. So you see here example for Paris, Berlin, and Berlin with a typo without an I. So you may ask, why 3 grams? Why not bigrams or 5 grams? It turns out that 3 grams work best for the English language. So if you have German words, you would probably use 5 grams because they work better for for the German language. Okay, this will make sense a little bit later when we combine everything. So let us show how the similarity calculation works. So we break down we have two strings and we break it down into trigrams. For the Paris-Berlin example, no trigrams are the same, so the similarity is 0. In case of Berlin and Berlin with a typo, missing an I, the distance is 0.5. So how does this work? You see on this Venn diagram, we have broken down those two strings into trigrams, and we simply calculate the common trigrams divided by the total number of trigrams. So in this case is there are 5 trigrams and total 10, so 5 divided by 10 is 0.5. So that's how we get the number. Okay, we will show an example of a city search. So we will try to search for some cities, and if we misspell a city, we will suggest the correct form to the user. In order to achieve this, we will have to prepare the data a little bit. So if we have a cities table, we will simply introduce another column called n-grams, and we will break each city down to the trigrams. Here in the slide, you can see how this looks like. So this is very simple, and even the TNT Search package has a helper function that will help you to break this into trigrams. So this is the data preparation part. Now, once we have this data, we need to store this somehow. In order to do that, we are using an inverted index. So some are familiar with it, but for those who aren't, so what is an inverted index? So if we have a bunch of documents, we'll take one document and break it into words. So you have a sentence and you break the sentence into words. So each word is then stored in the index with the document ID where it is located. So we have a document list and a posting list, so where each document is. So the word Paris is located in document 1. The word Berlin is located in document ID 2, and the London word is located in document 3. So it's a simple data structure that tells us right away where each word is located. Once we break this into words, we call them tokens. So we know where each token is located in which document. Okay, this is the structure, and TNT Search will also create the inverted index for you. So the workflow, how to achieve the suggestion did you mean functionality, is when the user enters a query. For example, let's say he enters the query correctly. So Berlin, we query the inverted index. The index returns some results, and we simply display them to the user, and that's it. So no problems there. But in case the user has a typo, we will query the index, and this time the index, of course, returns nothing, so empty result set. Then the engine will break down the user's query into trigrams. And again, we query the index, this time with a set of trigrams. And this time, hopefully, the index returns something. And we do some data processing after that and return the result set to the user. So this is the theory behind how it works. The tools to achieve this are, of course, Laravel, TNT Search, which is for creating the index and doing the search, and Laravel Scout, which is basically a wrapper around TNT Search to make it very easy to use. We won't cover the installation part because it's very simple. You do composer require Scout, and Composer require TNT Search, and you are ready to go. After that, you run scout import, and that's it. You have created the index. So what we're going, we will have the focus on the controller. So this is here the search method. So it has two parts. The first one is, like I explained in the diagram, in case the user spells the city correctly. So we are doing city search, the query of the user, and we get some results. So we are checking also if this is an exact match or not. If yes, we are returning simply the city to the user. In case the user makes a typo, we are asking the engine for suggestions. So the suggestion part. First, we take the query of the user and we build trigrams from the query. And then we ask the index to return some results for those trigrams. And the engine returns then all of those suggestions. Now, once we have those suggestions to have a more relevant result set, we will do sort by Levenshtein distance. So we are running it through this function. So here is how it looks like. We take the result set and calculate the Levenshtein distance. And if the distance is smaller than 3, we'll keep it. Otherwise, this does mean that you are allowed to make only 2 typos. So we will only return results that have 2 typos in it. And so this is the first part. And the second part is also a sort, but it takes also the population into consideration. So you may ask why the population is important for the cities, because there are a lot of cities that have the same name. I don't know, for example, if you knew that Berlin also exists in the United States. And yeah, if you search for Berlin with a typo, you will get as a first results, the Berlin that is located in the United States. And this is not probably the Berlin that you are looking for. So we are sorting it again by population because the German one is bigger, and yeah, it will be more relevant. And yeah, now the results are ready to be displayed to the user. We also created a demo that you can take a look at, located at cities.tnt studio. And you can try to search for any city. It will return you, hopefully, the correct results. So try simply with typo or something, and it will suggest you the correct form of the cities. The front end is on this page is built with React, but I guess it's not so much important. Probably you guys are more used to Vue.js since Laravel and Vue go better together. And yeah, it's basically a simple Ajax request to the server, and the server provides the results. Yeah, that's basically it. Any questions? We have this throw box, so if someone wants to catch it, Julie will throw it at you.
Thank you so much for the presentation. I had one question regarding the inverted lists. Where do you store them?
So the inverted index is actually a SQLite database. So TNT Search keeps track of this. Once you install code, you will have a config, and by default, it goes into the storage folder of Laravel. So the index is there. So it has the name, the model.index. And this is the inverted index, and it's basically a SQLite database that you can open with SQLite 3 command line.
And so it means that if you have multiple machines hosting your front-end servers, you have multiple times the indices on disk?
No, you have only an index for each model.
Yeah.
but you can make the architecture as you want. So you will always query the same index. You don't need to clone it multiple times.
Every single machine has one.
Yes, yes. Other questions?
You.
Hi, thank you
Hi.
so much for the presentation.
Thank you.
I'm a linguist, so I would be very curious to know if there's a database where I can find a number of grams that match each language.
No, actually, you have each time you have a data set, you have to create your own trigrams. So basically what you're doing, you're breaking words into trigrams. So it's language independent, this system. So you can use it for, I don't know, a product list or whatever you like. But for other cases, TNT Search uses a stemmer where we, for example, if you do full text search, we are trying to calculate the same root of a word.
Okay.
And we are storing it there. But we don't have a dictionary. We have for a couple of languages those stemmers for, I don't know, English, German, Ukraine, Russian, and Italian, and yeah. And this algorithm calculates the common root called stems.
Okay. Yeah, I know the term.
Yeah.
Okay, thank you very much.
Thank you. Come on, other questions? Again?
You are doing a lot of processing in RAM, especially the sorting step where you calculate the Levenstein distance, get the population, etc. Have you been testing TNT Search at scale?
Yes.
Like, how long does it take to answer a query on a CD index where you probably have like millions of
Okay.
of
Okay.
cities?
Let's go to the basic explanation of the inverted index. So this is basically a dictionary file where each term is a unique term. So querying it takes only 0.1 complexity. So in order to query any word, it has the complexity of 0.1. So if you break the word Paris into n-grams, it will only make 1, 2, 3, 4, 5, 6, 7 queries to the SQLite engine, and this is very fast. So a regular MacBook computer can do this in milliseconds. So it's very, very fast because the number of rows doesn't matter actually. It's always a 0.1 operation.
Yeah, but I assume then merging the inverted list of every single n-gram and doing the Levenstein distance, this is the
no,
consuming part.
It's not a problem. It's not a problem. You see, we are querying. Let me show you the code. We're taking only 500 most relevant from the index. So calculating the Levenstein distance, it is a complexity of n squared, but it only is done on maximal 500 rows. So it's not a problem at all.
And how do you choose the 500 rows to collect?
The engine does. So the engine behind TNT Search is Okapi BM25. So it's a best match algorithm, probabilistic algorithm for calculating the best results.
Okay. One last question.
En même temps. And all of that is configurable. The 500 rows you can take, you can make it 600, 5,000 if you will.
This part to take, yes. This is custom, but it also will have some limitations because not all of the trigrams are located in the index. So the complexity won't be a problem.
Yeah, of course. I just wanted to make sure the whole package is configurable. You can change the SQLite for PostgreSQL, for example, or
no, you can't. You can't because PostgreSQLite has also its own index. The idea behind TNT Search is to make it as simple as possible. So you don't need to worry about how the index is stored, where it is. you simply know that it will work. And the idea why SQLite, because when we started to build TNT Search, we tried our own data structure, B3 implementation, but SQLite seemed to be better because PHP has a built-in extension written in C that can communicate much faster than anything else. So it's fast as hell. Yeah. Thank you.